Good good afternoon, my dear warriors. Welcome to the Roar and probably one of the final sessions of the Roar series, uh, apart from the things which are lined up next week from Madan sir. So, my dear warriors, this is the most demanded session because I was seeing you guys spamming in almost every session, sir. We want alternating current, AC, AC, AC. So, finally, it is on, and we are going to see all the concepts and the applications and how to solve the questions as well in today's lecture. All right. So get set, go, guys. And for those of you who do not know me, well, my name is Captain Shreyas. I'm the physics master teacher, and I have been training and nurturing kids, guiding kids, sending a lot of students to their desired dream engineering colleges for more than 13 years now. And I'm extremely proud that thousands of my students are in the top tier 1 colleges. And most of these students were not toppers, they were just below average or average students. And that's what makes me feel extremely proud in raising a kid from average level to a level where he or she can go to a tier 1 college. So make sure you're subscribed to the number one J English channel in the country, which is the Vedantu J English, and make YouTube also know that listen, I'm interested in J, so keep me away from distractions. So by smashing the like button, or else they will recommend you all unnecessary stuff. Cool. Hi Prem, hi SEK, hi Krishna. I know this is a very unusual time for me to take the class, but circumstances demanded so. And it's okay. Some of you might even watch it recorded and it won't be a harm, even if you watch it recorded. And if you're watching it recorded, do let me know in the comments. Say hello, hi, yes sir, AC done, AC completed, whatever. Okay, in the comments after the video ends. So, to talk about alternating current, when I say alternating current or voltage, what I mean is basically the direction the direction of the current the direction of the current changes periodically changes periodically. It might be of constant value or not a constant value, but it changes with time. Once it goes clockwise, then anti-clockwise, clockwise, anti-clockwise. That is basically called as alternating current. Some of the examples graphically, if I like to show you of alternating current. See, if all these are basically current versus time, current versus time, current versus time, then imagine a graph like this or something like this or something maybe like this. If you notice, sometimes the current is positive, like you can see over here, like you can see on the upper side, and sometimes you can see the current is negative. When I say the current is negative, it means the direction is reversed. So all these are basically examples of alternating current. Periodically the current is reversing its flow, and the reason why this might be happening is because there might be a cycle of some procedures which might be occurring periodically, because of which the electricity is getting generated. Usually alternating currents are generated by rotating coils in a magnetic field, and because you rotate a coil in magnetic field, a cycle gets completed. So periodically you will see the direction will keep on reversing, and the exact same thing gets repeated again and again and again. And we know a rotating coil inside magnetic field produces electricity. Now the symbol of an AC source, the symbol of an AC source, like for a battery which supplies voltage, you use this symbol. For AC, the symbol goes like this. You show a circle and show a small wave like this. That's it. Remember, there is nothing like positive and negative for a AC, because alternatively one thing will be positive, then negative, then this will be positive, that will be negative. So this is basically the symbol for your AC source. I hope this is absolutely clear. Good afternoon, Akash. Hi, Sanjay. Nice to see you. Hi, Prem. Everyone, welcome aboard. Now, some of the basic terminologies of alternating current. So that's what we are going to see, the different terms in alternating current. Different terms in alternating current. First things first, very easy, peasy, lemon squeezy. See, if you have something which changes periodically, let's say like this, okay, then from here to here is one time period, one time period, basically t, assuming this axis horizontal is time axis. This could be either current or even voltage, doesn't matter, current or voltage. Okay, so that is basically one time period. Basically that is a cycle, a complete cycle that gets repeated, that gets obviously repeated. Then you obviously have the terminology called frequency, which is 1 by time period. So this is your frequency, and frequency is always going to be measured in hertz, just like in circular motion and so many other chapters, sound waves, waves, etc. Hertz is nothing but second inverse. And the last thing is omega, and that is basically your angular frequency, angular frequency omega, which is 2 pi by time period, or 2 pi into f, which is measured in radians per second, which is measured in basically radians per second. So if you know the time period of the cycle, you can measure the frequency. You can also measure the angular frequency of that particular alternating current. Vanakkam Darshan, nice to see all of you. This is the first term that you are seeing in alternating current. The next term that you need to see in alternating current is as follows. So say for example, this is our time. Let's say this is our current or voltage, whatever it is. And let's say this is our alternating current or voltage. Then this particular value, which you see right from here to here, right from here to here, this is called as the peak or maximum, or basically amplitude, amplitude of of that particular alternating current. Either the peak current, maximum current, amplitude, all of them mean the similar thing. Either you can take this or even this. Even this could be the same thing. There is no difference at all. This will be also like the amplitude. Usually the symbols that we use, usually the symbols that is used is like I naught, or let's say V naught, or even E naught. So this generally you use for current, this generally you use it for current, and this generally you use it for voltages. This generally you use for voltages. Sometimes instead of I naught, people also use I max. Sometimes here also people use V max or even E max. All these are the typical symbols that you will see in many of the books that you are going to use. IM or I max, I naught, V naught, E naught, VM, EM, E max, VM max. These are the typical symbols for representing the maximum variation, which is the amplitude, the maximum value of the current magnitude wise. Yes, that looks like a sine graph. Exactly. The this is a sine graph. You can even have graphs like this. This is like this is called as a square wave. This is a sine wave. This is a square because it square or looks like a rectangle. So, but it is called as a square wave. Don't ask me why. This is called as a triangular wave. Okay, or you can also call it as a sawtooth wave because it looks like the sawtooth when you cut through a knife or cut through a saw. The saws, the edges are going to look like this. So sometimes also called as a sawtooth or the triangular wave. This is generally called square wave. This is the sine wave typically. Next important factor which you should know, next important terminology which you should know is basically the average. Is basically nothing but the average value. So let's say this is our alternating voltage or current. Okay, so let's say this is current, let's say this is time. Okay, so you will have this value called as the average value. Average is nothing but the mean. Average or basically the mean average or the mean value. Average or the mean value. Now, typically, if you have countable number of terms, let's say 10 students are standing and you want to measure what is their average height, then the formula that you will use is you will add those numbers, height 1, height 2, height 3, like that, till the nth person, and then you will divide it by the number of terms. What you get is basically the average value. What you get is basically the average value. But this is okay if you have countable terms, 10, 20, 100, 1000, okay. But here, if you see the countable, the number of terms are not countable in such a continuous graph. The number of points that you have are infinite in number. So you cannot put plus over there. That will be replaced by a summation of infinity terms, which is then called as integration, which you all are aware of. So usually this formula that you will be using is nothing but integration of the current with respect to the time with definite integral limits from 0 to the time period upon the time period. So this is the typical formula for finding out the average value of the current, so or the voltage. This is for finite values. This is for finite values. This is if current or voltage is a function of time, or basically it's continuous. It's continuous with infinitely many values. Then you will be using this particular equation. This is the general formula. So I'm going to block this off because this is what is more likely you're going to use. This is not going to be used so often. Now, if you see this kind of a graph over here, then you will quickly realize for the above sine AC current, the sine alternating current, can you notice that the area under a cycle, the area under a cycle will always be 0. Whatever area will come over here, the exact same area will come here. This will be positive, this will be negative. So the total area will be 0, which means the numerator of this equation will be 0, which means integral of I dt from 0 to t, because remember this exactly is one time period, is definitely then going to be a big fat 0. So therefore the average current will also be 0. The average current will also be 0. Very, very important. Yes. So till I said 0 to time period. Can we find instantaneous value? Yes, the functions will be given, Akash. 11th standard upload mechanics of fluids. Vijay Kani, I am not going to make a lecture on mechanics of fluids. It will be taught in the crash course. But still, if you want my fluid classes on this particular channel only, just search for fluids. That's it. You will get my nurture playlist. So I have done question practice of fluids, zero to hero of fluids, and separate lectures on fluids over here in the nurture playlist. You can see it right over here. Yeah, Bernoulli's, hydrostatics, fluid mechanics, it's all done. Surface tension, everything is there. So you can check that out. Cool. Yeah. Will always be zero only for typical sine graphs. But if the area is not zero, then it will not be. Like for example, imagine I ask you, can you find the average current if the instantaneous current is 7 plus 3 cos 5 pi t? That is what the question is. What is the average current if the current is 7 plus 3 cos 5 pi t amperes? Okay, that is the question. Now you might be wondering, sir, how do we do this? I'll tell you, go by the graphs. It will become actually very, very easy. Then you will not face too much of a trouble. See, there is a cos graph. Cos graphs usually starts with a maximum value, then goes to zero, then negative, then zero, then maximum. Okay. So graph, a typical cos graph should have been like this. This is how a typical cos graph should have been in one time period. But there is a problem. There is 7 plus that cos function. That means this entire thing will be shifted up by 7 units. So whatever I have to show it up little bit. So it will go like this. It will go like this. And very importantly, this particular line, this amount by which I have shifted this up, this will be basically 7 units. Are you able to understand? Because 7 plus that cos function is there, and the amplitude of that cos function is 3. Amplitude of that cos function is 3. So this is basically 3. So 7 plus 3 cos 5 pi t. Got it, my dear warriors, till this point? Now think and tell me, when you try to find the average current, which will be by formula integral 0 to t by t of 7 plus 3 cos 5 pi t, okay, dt. I can split the integration if you want. So this will become 7 integral of dt from 0 to t divided by t plus 3 integration 0 to t cos 5 pi t dt, the whole thing divided by the time period. Now analyze this properly, use some knowledge of your definite integration and tell me what will the answer for this be. Well, for any sine, cos, tan functions, when you integrate it for one complete cycle, 0 to 2 pi like that, or things like this, one time period, obviously the definite integration will be a 0, because a cos graph for one complete cycle will have 0 area. So hence this answer will be a big fat 0. What is remaining is only this. Hence this will be 7. Integration of dt from 0 to t is t divided by t plus this big fat 0. Hence the answer will be 7 amperes. So this has no contribution in the average. Only this is now the average value. Is this clear, my dear warriors? Yes, this is obviously going to be enough for JEE. Can I use your flash series for my JEE main? Definitely. Sir, can I skip rotation motion only in the whole syllabus? I don't think, Senthil, you should skip that, because you have time. It's November still. Still December is there and little bit of January is there. I think easily within 3-4 days, you can complete some aspects of rotation at least, and maybe later on once you can watch one shot or something and further advance your knowledge. But don't skip rotation. You have time. Okay, very good. Nikhil caught up. Awesome. Great, clear, Sanjay. So this is how you can find the average values of currents or voltages. So that was average. Now you might be wondering, why do we need average? The reason for that is, note this very important point which I'm going to give you. A DC voltmeter or ammeter measures the average value of an AC. This is very, very crucial. What do I mean by that? Let me give you an example for this. Imagine you have an alternating source over here and you are having an ammeter, and maybe you are also connecting a voltmeter over here, and maybe this is connected to some kind of device over here like this. This is a alternating current. If you use a DC voltmeter or ammeter, what do I mean by DC voltmeter or ammeter? A DC voltmeter and ammeter is based on, it is based on the principles of magnetic effects of current based on the moving coil galvanometer. Moving coil galvanometer. And we have seen this already, how you can convert a galvanometer into ammeter or a galvanometer into voltmeter. So imagine, once the current passes this way, then the current passes the other way, the galvanometer will start fluctuating, and then it will not be able to move. Before it decides to move, the next cycle has appeared, the next negative half has appeared. Before it decides to move negatively, the positive half will appear. So it will end up maintaining the average value. So whatever is the average, that is what these things will show. So the voltmeter and the ammeter will definitely show, the voltmeter will definitely show the average value of the voltage, and the ammeter will definitely show average value of current. Is this clear? Typically it will be 0 because you will normally have sine voltages or currents. So for sine voltages and currents, what is the average value? It will be typically 0. So it will not show any reading. It will show 0 volts or 0 amperes. So you might be shocked looking at that voltmeter. Oh my God, sir, this is a AC current, but my voltmeter is showing a wrong answer. So it's not showing wrong answer. It is showing correctly. It's just ending up showing the average value. Okay. I hope this is absolutely clear. Great. Light waves, I think it was done by Madan sir, if I'm not wrong. Nikhil? Yeah, it should be done by Madan sir. Yes, over here. Just go back a little bit, right over here. I think before nuclei, electromagnetic waves. Yeah, so in this only, everything was done. So just have a look at it. This waves chapter. Okay. But still, if you're specifically looking for light waves, you can just search for light waves again over here. You will be able to find my lecture only on light waves, Huygens principle, diffraction, photons, wave particle duality, wave optics 0 to hero, everything is there. Okay, you can find that. Okay. Now, having said this, let's go ahead. The next important parameter that you need to study in alternating current, and that is basically your RMS, and this is the most important parameter, also called as the root mean and the square. That is the short form for that. Root mean square RMS value of current or a voltage. Now what is this RMS value? Let's understand this with a simple example. Say my dear warriors, you have, say you have, okay, perfect. Say you have a resistance. Say you have some kind of resistance. Okay. Now, in this resistance, let's say somebody is passing an alternating current. Somebody is passing an alternating current. So what will happen is, once the current will go like this in the positive cycle, the current will go like this, and then in the negative cycle, the current will change the direction and it will go like this. So tell me one thing. Okay, let me just draw the graph over here. So it will have a positive half cycle, then it will have a negative half cycle, and this thing will obviously continue. Is it that during positive half cycle, the current will generate heat, and during negative half cycle, instead of generating heat, it will absorb the heat? Is that so? Think and tell me in the chat box. I'm so glad you are comparing me with such an amazing scientist. Thank you so much, Ajay Pranav. And probably because I love physics, that's all. Do you think the current which passes through the resistor during the positive and the negative half cycle, in positive it will generate heat, in the negative it will absorb the heat? Is that so? I don't think so, because remember, the heat generation formula is I squared R, so the sign of I doesn't even matter. Well, that's mathematically. But otherwise also, why should the direction of the current in a resistor decide whether heat is generated or absorbed? The moment current passes through a resistor does not have a directional property in it. So whether the current goes like this or like this, it will end up generating some amount of heat. So it's not like it will generate and absorb, or absorb and generate. No, it will generate heat. So in both the cycles, in both the half of the cycles, heat will be generated here also as well as here also. Now, how much amount of heat was generated? I cannot use I squared R formula. In one cycle, I cannot say I squared R, because the I itself is changing. Once it is 0, then some value, some more value, maximum, some value 0, some value, some more value, some less value, again 0. So every instant the current is changing. But then that is the reason why we get this RMS term. Imagine I use that same resistance, but this time I attach it to a DC circuit, and I end up passing a constant current in it, such that when that current passes, the amount of heat which is generated is exactly the same as that of the AC current. Such constant current which generates the same heat, so this constant current generates the same heat in the same resistance as that of the alternating current, which is variable in nature in a cycle. That constant current is then called as RMS. That constant current of the DC, which can be used for heat calculations, and you can replace that AC with this constant current, and it produces the same power, same energy losses, is then called as the RMS value. So this constant current is then called as the RMS value of the current, RMS value of that particular current. Is this absolutely clear, my dear warriors? Now, this RMS current, believe me, it won't be as high, it won't be 0, it will be somewhere here. It is that constant current for that same time in that same resistance, which is now going to generate the same amount of heat. So this value is then your IRMS. Is this absolutely clear? What is the meaning Forget the formula, I have not even come to the formula. The meaning of the RMS current is that constant current which generates the same heat by DC as that generated by a variable alternating current. Cool. Give me a thumbs up if this is understood. Absolutely clear. Let me know, my dear warriors. And I hope you guys are smashing the like button. In case you forgot, please do that right away, right now. Many people keep watching the class, get involved, and forget to like. Okay. Thank you so much for liking. Great. Now, how much is this value of RMS? Now, whenever you have to find the RMS value, I'll tell you, always go reverse, read it in reverse, square, mean, and root. So, whenever you have to find the RMS, what you will do is basically first square the values. Let's say you have to find the RMS height of 100 students or n students. You will write height 1, height 2, like that, height 3, like that. So I1 square, I2 square, I3 square, like that, till whatever, IN square. Then you will take the mean, read it reverse. First square the values, then mean. Mean means average. So how do you take average? Add all these numbers and then divide it by the number of values. In the end, what is their root? So then take the root of it. So that is how you find RMS value of anything, be it current, voltage, height, speed, acceleration, force, whatever RMS thing you have to find, this is the formula. Okay, read it reverse, square the values, then take the average by adding and dividing by n, and in the end take the root of it. But this is only going to be useful if you have finite number of values. This is for finite number of values, but typically the number of values might not be finite. So then what you do is basically you do integration I squared dt from 0 to t, the whole thing divided by t. This is like taking the average of I squared and eventually put it inside the root. So this is how you do it. All right, so this is the formula for continuous value based functions, and this is what will be more important for you. So this is what you will use for continuous values or functions. Continuous values or functions. Integral I squared dt 0 to t divided by t, whole thing inside the root. If you don't like inside the root, you can put I squared RMS over here, so it looks a little bit easier. So if, say for example, we are talking about a sine graph for a sine alternating current, the current value will be something like this: I naught sine omega into t. Makes sense, because this is how the graph would look like. This is how the graph would look like. This would be the current, this would be the time, and the graph will go like this. Correct? It will increase, decrease. It's a sine value. So this would be basically your I naught. This thing will be basically your I naught. I naught sine omega t. How do I find the RMS value for that? In order to find the RMS value, use this particular formula and let's solve it. So IRMS square will be integral I squared dt by t from 0 to t. So basically over here, I is nothing but this one. So it will be I naught square sine square omega t from 0 to t divided by t. Then what you will do is basically I naught square is a constant, so comes outside. What can you do with sine square? You can't integrate sine square, but you can use the double angle formula for cos. Cos to theta, yes, is 2 cos square theta minus 1 or 1 minus 2 sine square theta. So therefore sine square theta will be nothing but 1 minus cos 2 theta divided by 2. So therefore I naught square by t, and then I will put integration 0 to t 1 minus cos 2 omega t, the whole thing divided by 2. Oh, dt is also there. Yes, this is what it will look like. I can separate out the terms. Yes, definitely. So this will just become I naught square divided by t 1 by 2. So 1 by 2 dt. So dt by 2. So dt by 2 integration 0 to t minus I naught square by t. I naught square by t, and you have negative dt by 2. Okay, so negative is there already, dt by 2. So integration 0 to t, and cos is also there. So cos 2 omega t dt, the whole thing divided by 2. This is what it will look like. I have just separated out the terms, nothing great about it. Now, rotational motion was done. I have already done it, Manjari. Even in the crash course, I just recently took it, and yes, I have already done the rotation motion on this channel. It's there in the videos or live section. You can check out the playlist. It's there. Okay. What is integration of dt? It is basically t. So it will be I naught square t by t, and this is multiplied by 2 minus this is I naught square by t, and here you have 2. Integration of any cos sine function over a period is always going to be a big fat 0, guys. So 0 into anything is 0. So forget that, tt cancels. I'm left with I naught square by 2, and that is basically your IRMS square. Therefore, the RMS value will be I naught by root 2. Now, 1 by root 2 is approximately 0.707, which you should remember as a value for ease of calculations. Now, this is something which I believe you should remember, because it will be useful for many problems, because most of our problems will be sine or cos functions only. So that's why you should remember this. Is that okay? I hope this is absolutely clear. Is there any easy method for this? Well, there is no easy method for this. Unfortunately, you have to do this integration. Okay, there is no other way out of it. Unless you remember the value of integral of sine square. It's like there in your head. So, I mean, the shortcut will be you remembering some integral value. But that is not really a easy method. It's just you're remembering something. Now, let's see if some of you can answer this particular question. This was asked in many of the examinations. The current is 3 sine omega t plus 4 cos omega t. Find the RMS. Find the RMS. That is the question. Find the RMS value. Okay, now typically for just a pure sine function, it will be maximum by root 2. But here, it's not just a sine, there is a cos also, and they are added. How are you going to do this question? Now, typically I've seen many books do this. To find the RMS value, what they do is use the formula 0 to t of current. Current is basically what? 3 sine omega t plus 4 cos omega t whole square dt, the whole thing divided by time, that is IRMS square. Just imagine how long this will be, because there are two terms, you're squaring it, all sorts of nonsense. This is just going to be very, very long. I would avoid this. I don't like this. Instead, what I will do is I will use little bit of mathematics knowledge. Obviously, you cannot say, sir, I learned that in maths under Namrata ma'am. I didn't know that we can use it with you in physics. There is nothing like that. If you learn something, you have to use it. It doesn't matter where you learned. You might have learned it in biology also. If you can use it anywhere, that's it. I hope this is clear. So, my dear students, what we can do is, whenever you have such a function, this is of the form current is A sine theta plus B cos theta. This can be always written down as root of A square plus B square into sine theta plus some psi or phi or whatever value you want to take. Remember this? You would have done this in trigonometry, maximum minimum value of A sine theta plus B cos theta. So that means even this function can be written down as root of A over here is 3. square plus 4 square. Sine of theta over here is omega t, and plus psi. Doesn't matter what that psi is. It really doesn't matter. 3 square 9, 4 square 16, 9 plus 16 25, root of 25 is 5. So current is basically 5 sine omega t plus something. This is basically the maximum or the peak value. Therefore, the RMS value will be the peak. Remember, peak divided by root 2. So it will be 5 divided by root 2 amperes. That is the answer. Directly you can do this, and we have avoided all this long integrations and all that nonsense. Very simple and easy stuff. Yep, very good. Modern physics already done by Madan sir. Yes, already done. Yep. Semiconductors already being done by Madan sir. My old classes of semiconductors and modern physics already there on the channel. You can check that out again. Okay, cool. Great. So that was RMS. Now you will be like, sir, why RMS? Why did we learn RMS? One advantage is it helps us visualize that alternating current in terms of a constant current, which is delivering the same power. But the main thing is, remember, the thing about RMS is, all alternating currents values, unless mentioned otherwise, unless mentioned otherwise, are in RMS. Also, you will see hot wire instruments measure that RMS values, measure the RMS values of your alternating current. What do I mean by that? See, you use any appliance, maybe AC, fridge, whatever, or you go to some other country and you see the voltage rating. All those voltages which they give are never the maximum or the average. They are always the RMS values. They are always the RMS values. So typically in India, when we say the household voltage, the house voltage is 220 volts and 50 hertz. What does it mean? What does it mean? It means that this 220 volts is basically RMS value. So in fact, if you want the maximum value, remember maximum by root 2 will be 220. So the maximum value of the voltage will be 220 multiplied by root 2, which will be approximately 310 volts. So in our houses, though it says 220 volts, that's the RMS value, which is not the maximum. The maximum is actually slightly more than 310 volts. That's a very different thing. So nothing has been mentioned. When nothing has been mentioned, it is always RMS. That's what I mentioned over here. When nothing is mentioned otherwise, always RMS. Whenever you use hot wire instruments are what? They are those instruments which are used to measure alternating voltages and currents. See, I can't use DC voltmeters and ammeters for AC because they will always give me zero reading, average values. So how do I measure AC? There is a different mechanism altogether. We don't have it in the syllabus, but they are based on the heat and power losses calculation. So using those hot wire instruments, you can measure, oh, this much voltage is there in AC, this much current is there in AC. So those instruments always end up measuring the RMS values. Is this absolutely clear, my dear students, how this goes? Cool. Shall we go ahead to the next one? Shall we go ahead to the next concept? Perfect. So we have learned RMS, how to do the calculations. We have seen how to do the average calculations. We have seen frequency, time period, and in general definition of AC and the symbol. Now, what happens is in typical AC circuits, the voltages and the currents may not be in the same phase. Meaning, say for example, if you have let's say some device over here, and let's say there is some current, there is some current which is passing through it, and across it you are measuring some voltage. Across it you are basically measuring some voltage V between this point and let's say this point. It might usually happen if it is alternating current or alternating source is there. If there is an AC source, okay, if there is an AC source and the currents are alternating in nature, what you might typically see is something like this. If you draw for maybe let's say current, maybe the current graph is like this. So maybe the current is I naught sine omega t, just like your SHM equation. But maybe the voltage graph may not be like that. Maybe it is going to be like this. It's not in sync. There is some kind of phase difference. So maybe that voltage will be V naught sine omega t plus phi. This phi is nothing but this particular phi that you see over here. This is nothing but the phase difference, the phase difference between the voltage and the current. Between the voltage and the current. They might typically not be in sync. So if you remember phasor diagrams tell me about the phase, the difference of phases, who is leading, who is lagging, etc. It might typically look something like this. Maybe the phasor of current, maybe the phasor of current is over here, and then the phasor of voltage might be like this. So this might be the voltage phasor, this might be the current phasor, and there might be an difference between the two, which is basically phi. So this is what it might look in the phasor diagram. It tells me the difference of the phases, and these two things will obviously be rotating together. These two things will be rotating together like this with a common speed of omega. So in alternating circuits, what did I just mention? The currents and the voltages typically may not be in the same phase, because of which there is a phase difference and the calculations become necessary in terms of the phases. Phi is usually the phase difference between the currents and the voltages, and uh, it is usually represented in the phasor diagram very easily. In the time graph also you can see it, that yes, they are not reaching their maximum or their least or their zeros together. There is some delay between them, but the exact amount we can calculate it very easily in the phasor diagram. Is this okay? Yes. Great. Sir, I'm so glad, Aditya. Thank you so much. I want to take that EET test. I want to take that once integration. Abhinav, I'm not able to understand what you're saying. Sir, Sunday we have exam from 10 a.m. to 1 p.m. Okay. I didn't really get what is the concern, dark night. If you have the exam. Now, how much is this phase difference? How do we know it? How do we calculate it? So there is a simple way of doing it. So let's have a look at it. Now, remember, any circuit, any device around us has one of these three characteristics around it. It might have some resistive characteristic, resistance. It might have some inductive characteristic. It might have basically, a capacitive characteristic. So basically this device which I'm talking about has the following characteristics. Number one, it might have some resistance R. Number two, it might have some inductance L. It might have some capacitance C. These characteristics decide, whatever these characteristics are, they decide the phase difference. How much inductance is there, how much capacitance is there, how much resistance is there, all the three together, they decide that phase difference. Is this absolutely clear? Give me a thumbs up in the chat box right now. Well, if you have an exam on Monday on this topic, then nothing better than attending this class. Trust me, because the entire topic will be covered in today's lecture. Cool. So what did I just say? That listen, all the voltages and currents in alternating AC circuits are typically not in phase. So there is a phase difference, and that phase difference depends on the device. It might have some resistance, it might have some inductance, it might have some capacitance. So based on that, the gap might increase or decrease. All these things, the angle between voltage and current phasor might increase or basically decrease. So the derivation is not needed, Afifa. I would suggest it is not needed, definitely, but from board's point of view, yeah, little bit, but otherwise it's typically not needed. But I feel that it should be done over here because for advanced it will be useful and you will understand how things are happening. It won't take me much time. I'll just show you two things. You will understand automatically the third thing. So let's take an alternating circuit with basically resistance and see how does it exactly behave. So say for example, we have this AC source, okay, like this, and the voltage is basically V naught sine omega t, and now that is connected to a simple resistor, nothing great over here, that's it. And now in that resistance some current will pass, this is that current. So using our Ohm's law, one can directly say, so using our typical Ohm's law, one can say that, listen, the voltage of that particular source is also the voltage across that resistor, and the voltage across the resistor is current into resistance, is nothing but the current multiplied by the resistance. What is the voltage of that source? It is nothing but V naught sine omega t at any given instant. So from this, if I try to find what is the value of the current, R will go below, and what I have over here is V naught sine omega t, the whole thing divided by R. Now, looking at this, I have an idea what I can do. So let's say I write current is equal to, well, V naught is a constant, R is a constant. V naught is a constant, R is a constant. So let me put V naught separately, sine omega t separately, and this resistance, let me put it below R. This is some constant into sine omega t. Oh, so that means I can just think of it as if this is I naught into sine omega t. I naught into sine omega t. Where our where our I naught is nothing but what? V naught by R is nothing but the voltage divided by the resistance. Exactly what you would expect. Current is voltage by resistance. That is what you would expect by even Ohm's law or any other Kirchhoff's law. If you now draw the graph of currents and voltages, how will it look like? Currents and voltages, how will it look like? Well, the current graph is a sine graph. Even the voltage graph is a sine graph. So I think it will look like this. This is current, let's say. Okay, this is current. Even the voltage graph will look like this. So that is your voltage. Can you see both the current and the voltage and the voltage? What are they? Are they having any phase difference? No, they are in phase. They are in phase. That means phi is 0. So if one had to draw their phasor diagram, the phasor diagram would look something like this. If you show current over here, the voltage phasor will be like overlapping it, will be overlapping it. This is the voltage phasor, this will be the current phasor. You can see they are overlapping each other. That means there is no phase angle difference between them. Is this point absolutely clear how alternating current behaves with a simple resistance? No change in the phase. Both current and voltage are in sync. So now this must give an idea. Sir, if resistance does not cause phase change, maybe inductance and capacitance will. And exactly that's what happens. That is the next point that we are going to see. Okay, everybody with me? Everybody in with me? Yes. We are going to come to LCR circuit. First, let's see each of them individually. So, if you have an alternating circuit, let's say with capacitor, example, alternating circuit with, let's say, capacitor. So, this is our capacitor. There will be some current which is passing. Okay. Now, let's say for example, we start by this logic that, listen, Q is equal to capacitance into the voltage at that instant. Q is equal to C into V. Is that okay? Q is equal to basically C into V. And let's say the voltage just happens to be V naught sine omega t. V is equal to V naught sine omega t. So substituting the value of voltage, I will get this as V naught sine omega t is nothing but the charge which is capacitance into V naught sine omega t. This charge will depend at which time you are seeing it. So the charge will keep changing with time. Therefore, if I try to find the current is nothing but rate of flow of charge, dq by dt. So when I try to find current by differentiating q, what will happen? The capacitance value will come outside. Even V naught value will come outside. Capacitance and V naught will come outside. And what will be left is just the derivative of this term over here, which is nothing but sine omega t. So dq by dt, right? So derivative of this guy. Capacitance outside, V naught outside, derivative of sine omega t. Everyone clear till this point? Okay. All right. If the resistance is between 0 and 1 ohm, just that the heights will interchange. So don't take it literally, sir, always voltage graph will be more than the current graph. No, it is just a generic. We have to show something. No, that's all. That's the reason. Okay. So it's just like, sir, you ask me, show a boy and a girl. Okay, fine. Sir shows a boy and a girl like this. Like, no, sir, the boy can be shorter, the girl can be taller, sir, the boy can be fatter, girl can be short. Yeah, all these are possibilities. It's just a representation. So don't take it literally that always voltage will be more than current. No, it depends obviously, because R can be more, can be less, depends, right? So this is just a representation. Okay. Now coming back over here, derivative of sine omega t will be nothing but omega will come outside and we will have cos omega t, of course. And this V naught is there as it is. this capacitance is there as it is equal to therefore the current. Now I have an idea what we can do. Usually current is voltage by resistance. Usually current is voltage by resistance, right? That's what we know. Current is voltage by resistance. Current is voltage by resistance. Voltage by resistance. So it is not looking like that right now. So maybe I will have to convert it in the form that I wanted to. V naught cos omega t. V naught. I'll put cos omega t over here, divided by voltage by resistance. Nothing to divide, everything is on the top. So I have no other option but to write it like this, 1 by C. If I write 1 by C in the denominator, C will go in the numerator eventually. Omega is also in the numerator. Bring it in the denominator like this. So now it looks like voltage by resistance into some time varying term is equal to current. So now I have, therefore, the current is, this is a constant, omega C, V naught, all of them are constants. So it is I naught, and then this will be nothing but cos omega t. Now, the moment you get this, you will start comparing and see what the hell is this I naught. This I naught is nothing but this V naught divided by this guy, which is C omega. It is not looking like a resistance. I want current is voltage by resistance, which means whatever I written here is like resistance, but not an actual resistor. Capacitance is not a resistor. Capacitance is a capacitor. Correct? Simple. Bitzian is not a NITN. NITN is not a Bitzian. NITN is behaving like a Bitzian. Bitzian is behaving like a NITN. That's a different story. Getting my point? So we cannot call it resistance, but it is behaving like a resistance. So we introduce a new term and we therefore call it as reactance. We call it as a reactance. And who is behaving like the resistor? Capacitor. So we call it as the capacitive reactance. The symbol for reactance is X. Since it is capacitive, put C in the subscript. XC is nothing but 1 by omega C. The unit is still going to be ohm. So therefore, what do I get? The current is still the voltage, but by resistance? No, reactance. And who is reactance? Capacitor's reactance, XC. So current is voltage by capacitive's reactance. Reactance is like resistance, but not an actual resistor. Got it? Hello, Janu. Welcome, everyone. Till this point, absolutely clear. What is the meaning of reactance? Unit is still the same because it behaves exactly like a resistor. Okay, right? Now, one more important note is that reactance, or basically XC, this is very important, capacitive reactance doesn't cause power loss. Very, very important. Power loss, even if it opposes the AC current. Even if it opposes the AC current. So, see, it has some characteristics of resistor, like it opposes the current, but it is not causing any loss. Why? Because capacitor can never cause any loss. Capacitor has electric field inside it, and electric field stores that energy. So because it faithfully stores and restores that energy, that's why it cannot cause any loss. So mind it that it does not cause any power loss, but it definitely opposes the AC current. Keep that in mind. Yeah. No, it is not radian per second. It is ohm. Okay, right. Similarly, okay. Now, if you see over here, if I draw the graph versus time for current and voltages, voltage graph is a sine graph. Voltage graph is a sine graph. This is voltage. Current graph is a cos graph. It could be smaller, it could be lesser, more, I don't know. Just showing some. Always get confused in drawing these. So this is basically your current graph. You can see they are definitely not in the same phase. In fact, if you show a phasor diagram over here, you will quickly realize that if the voltage phasor is like this, the current phasor, oops, the current phasor will be like this, and the angle between them will be 90 degree. Yes, angle between them will be 90 degree. This is current, this is voltage. How do I know that? Because see, when voltage is zero, current is already maximum. So current is ahead. Current is basically ahead of the voltage by 90 degrees. So here I can say that the current leads whom? The voltage across whom? A capacitor by 90 degrees or pi by 2 radians. Very, very important. Leads means it is already ahead of it. Cool, guys? Yep. Very good. So by the same logic, if you apply alternating current with an inductor, it should be now very obvious to you what might happen. This is your inductor. Let's say this is your current. You will see something like this. This time, it will be exactly reverse. Yes, the current graph will be a sine graph. And the voltage graph will be a cosine graph. So this is your voltage graph. Here, if you show the phasor diagram, if the phasor of the current is, if the phasor of the current is like this, you will see the phasor of the voltage will be over here. So, and this would be 90 degrees. Here I will say the voltage across an inductor, the voltage across an inductor leads by pi by 2 radian with respect to the current. with respect to the current. So voltage is ahead of the current by 90 degrees across the inductor. So think about it. Just like before, we used to write, where did it go? Yeah, here. Current is voltage by reactance of the capacitor. What will I write over here? I will say that the maximum current is nothing but the maximum voltage divided by the reactance but of the inductor. So this will be then called as the inductive reactance. Again, measured in ohms only, no difference at all. Just like capacitive reactance was 1 by omega c, everything is opposite now in inductor. So you will see instead of 1 by omega c, it will be omega. There is no capacitor, there is inductor. So it will be just omega L. So XL is actually omega L. So this is the formula for it. So all these things you better remember, my dear warriors. All these things. What is capacitive reactance? How current is related to reactance? All these things. Is this absolutely clear? Again, just like before, you will see XL doesn't cause power loss, but it opposes, but definitely it opposes the AC current. It definitely will oppose the AC current, like you can see over here that this resistance like behavior is coming in the inductor and it is reducing the current. If reactance is more, current will reduce, so it resists the current, but it is not going to cause any power loss because it will faithfully store the energy inside the magnetic field of the inductor. Okay, I hope this is absolutely clear. Yep. No, there is 12th and 11th. Right now, 12th portions might be going on priority. 11th portions are also there. So it will go on. Don't worry about it. Just because 12th classes are continuing does not mean 11th is not there. Both syllabus is there in the JEE 2025 crash course. Now you might be wondering, sir, fine, I understood what happens with the resistor, what happens with inductor, what happens with capacitor. So with the resistor, there is no phase difference. With capacitor, there is a difference of 90 degrees. Current is going ahead by voltage. And in the inductor, voltage is going ahead with respect to the current. What if all three are there together? So that's why we have alternating current with LCR circuits. What will happen then? Let's have a look at it. So let's say we have a AC source like this, and then we have a resistor, then maybe a capacitor, then maybe an inductor, something like this. What happens is you measure the voltage across resistor, you measure the voltage across capacitor, you measure the voltage across inductor like this. Also, you might have an ammeter in the circuit. You will notice since the devices are in series, whatever current is flowing will be the same. So the current is same in series. Current is same because they are in series, but voltages may not be same in series. Obviously, we know that. So what do we do? Well, the total voltage of the circuit, let's say I call it as V, which is given by the source. Lot of you might now think, sir, it is very simple. V is VR plus VC plus VL. Yes, correct. You are right. The voltage in the circuit as a whole, okay, at an instant. This is the net voltage at an instant of time. That will be equal to whatever is voltage across the resistor at that time plus whatever voltage is there across the capacitor at that time plus whatever voltage is there across the inductor at that time. But usually we don't worry about instantaneous voltages in AC. When was the time last where we worried about instantaneous voltages? Like I told you about, in India, household voltage is 220. Where do you bother? Oh, now it is 199, now it is 198, now it is 197. What you generally care about is RMS, or just the average, or just the maximum value. That's what you usually care about, right? You're just caring about the maximum voltages, RMS, peaks. This is what you generally define AC in terms of. So I am not generally interested in adding the instantaneous values. I'm generally interested in the actual values, which I will measure using a voltmeter, or basically maximum RMS, those things. So now tell me, if the maximum voltage across the resistor is VR naught, maximum voltage across the capacitor is VC naught, maximum voltage across inductor is VL naught. If I add all of them, should I or should I not get the maximum net voltage across the circuit? Yes or no? Come on, put it up in the chat box. Glad, Janu, you're enjoying it. Is there any scope of theory bits in AC? Theory bits in AC means? What do you mean by theory bits? Yeah, come on, think and tell me. Will this be equal? The answer is absolutely not. Definitely they are not going to be equal, because you'll be like, why they are not equal? When this is maximum, what guarantee this is also maximum? What guarantee this is also maximum? Why they are not necessarily going to be maximum? Because they are not in phase. Remember, voltages across resistor, inductor, capacitors, they might go behind in sync, they might be ahead of the current. So the current is same in all of them, but the voltages aren't, which means I can't add their maximum voltages as it is, since they are not in phase. I can't do that. I can't do that. So the only option left with me is, whenever you have such things which are not in phase, a wave added to another wave, added to another wave, what do you generally do? You have learned this in superposition of waves as well. Example, say you have to, add 2 sine 15 pi t plus 3 sine 15 pi t plus pi by 6 plus 4 sine 15 pi t plus pi by 2, something like this. What you will do is, you can actually write this down as something sine 15 pi t plus something. What is that something? Let me tell you that. What you do is concentrate your attention on what is there outside the sine term. These are the amplitudes, the maximum values 2, 3 and 4. Treat them like vectors of those lengths, length 2, length 3, length 4. Next thing, concentrate your focus on what is added to 15 pi t. Here nothing is there, plus 0. Here it is plus pi by 6. Here it is plus pi by 2. Those are going to tell me the directions of those vectors. So draw a vector of length 2 in 0 degrees, meaning pointing in the right side along x-axis 0 degrees. His length is 2. Then show a vector of length 3 making an angle of pi by 6 radian, meaning how much? 30 degree. So this is a vector of length 3, and yes, this angle is just going to be pi by 6, or basically 30 degrees. Then show another vector of length 4 making an angle of 90 degrees with respect to the original direction. So 90 degrees is basically something like this. So this is having a length of 4, and this is basically pi by 2 radian. These are now vectors, but they are not actual vectors. They were forcefully made into vectors, so that's why they are called phasors. That's why we study phasor diagrams, because you can use the properties of vectors. So whatever resultant you get over here, whatever resultant you get over here, okay, I don't know, I'm just chumma saying some resultant you might get, some resultant r, and maybe this angle will be phi. Whatever resultant you get over here will be here, and whatever phi you get will be over here. That's it. So that is how you add multiple sine or cosine terms with phase difference and different amplitudes. So tell me, how is this different from this over here? This are sine cosine functions with different amplitudes and different phases. I have to add them, which means I have to do vector addition of the phasors. Got it? Which means I have to do vector addition of the phasors. Niranjan, point noted. KTG is important, yes. So that is the reason why I will say, hence V naught bar is equal to VR naught bar plus VC naught bar plus VL naught bar. This is how it actually goes. This is correct. Since they are not in phase, I have to add them like phasors. So vectors. So the phasors are added like vectors. This is correct. There is nothing wrong in this. So you might ask, okay, sir, how are the phasors going to look like? How are the phasors going to look like for them? Let's have a look. First of all, we will show the current phasor because current is the same in all of them. So this is the current phasor. This is the current phasor. Voltage across the resistor is in sync with the current. So I will show basically VR naught over here because resistors voltage and current are always in the same phase. We have seen that right over here. Current and voltage are in the same phase. But when you go to capacitor, you will see, sorry, this is inductor. For capacitor, the voltage is behind the current. For inductor, the voltage is ahead of the current. So keeping that in mind, I can show one line like this and maybe one line like this. This is voltage across the capacitor. This is voltage across the inductor. This could be more, this could be more, anything could be more. Here I have shown inductor's voltage to be higher, but there is nothing wrong in showing it to be less. I have to show something more and something less, no? That's why. Okay. So this is how the phasor diagrams will look like. Now I have to add these three phasors by treating them like vectors. How do I add these three vectors? Obviously, I will first take care of these two because they are along the same line. If this is bigger, this is smaller, the remaining thing which I will get is only this much. And this will be VL naught minus VC naught. I don't know who is more, who is less, so I'll put a mod symbol over here. The remaining phasor is still there, which is VR naught, of course. And the current phasor, how can I forget? It is still along the resistor's voltage. Okay, this is how it will look like. Now I have to add this and this, this and this. When I add this and this, use parallelogram law. Yep, use parallelogram law to add them. You can also use triangle law by shifting this over here. One and the same thing, guys. Whatever you do, you will get this. And this would be the total voltage. This would be the total voltage. That is what we were expecting, right? This is basically this plus this plus this. So this is your total voltage V naught. Now, because of Pythagoras theorem, can you not see V naught value will be root of, think about it, base, which is VR naught square plus this square. So that is nothing but VL naught minus VC naught square. That is what it will be. Okay, so this is the value of the net voltage in terms of the other voltages of maximum values across resistor, inductor and capacitor. Also, one can easily say, that the net voltage RMS across the entire circuit will be the voltage across the resistors RMS value you take square plus voltage across inductors RMS value you take again minus voltage across capacitors RMS value you take and then square it. If you use RMS here, use RMS. If you use maximum, use maximum. That's how it goes. It's one and the same thing. Now, can you see with the net voltage, the current is making an angle over here. The current is definitely making an angle with the net voltage. That is your phi. And this is what I was telling you before. The current and the voltages usually are not going to be in phase. There is going to be a phase difference. It depends on all the three elements of that device: inductive, resistive, and capacitive property. So as you can see over here as well, the resistor, inductor, and capacitor, all three together play a role in phi. That is your phase difference. So therefore, one can easily say tan of phi opposite by adjacent. Opposite is VL naught minus VC naught, and adjacent is nothing but VR naught. So that is basically your tan phi, which will give you me the phase difference. The phase difference between the voltages and the currents. Cool? Okay. Now that I have got till here, I will not stop there. I will do one thing. See, VR naught, VC naught, VL naught voltages are currents into resistances. So current into resistance. So what is the resistance? Across resistor, this will be R, this will be XC, this will be XL. XC is nothing but 1 by omega C, XL is nothing but just omega L. We have seen this just some time back. Voltage is current into resistance, voltage across capacitor is current into capacitive reactance, voltage across inductor is current into inductive reactance. How about substituting these over here? Over here. Observe now carefully. I'm going to substitute over here. So what am I going to get? Let's see. So V naught is equal to root of, instead of VR naught, I'm going to put IR. I'm just going to put current into basically resistance. This thing will be squared plus, here I'll have something minus something, the squared. That's what it will be over here. What is that something minus something? Current is definitely there, and here I will have XL and here I have XC. So that's what I have put over here. Instead of VL and VC naught, I'm putting IX over here and then squaring it in this particular root. As you can see, I square will come out common. I square will come out common. And here we will have a big root. Okay. And inside the brackets, what will I have? I will have R square over here, and here I will have plus XL minus XC whole square. Okay, and this bracket complete. I square's root is basically I, so I can just put I over here outside. So this voltage is I into, and here I have basically a root of R square plus XL minus XC whole square. Somehow I am getting very much tempted now. Voltage is current into resistances. Voltage is current into resistance. So shouldn't the total voltage also be the current into the resistance equivalent, current into the resistance equivalent. But you will be wondering, should I write resistance or should I write reactance? Because the total thing will neither be a resistance purely nor be a reactance. It is a combination of resistance and reactance. That new thing is then called, that new thing is then called as Z, which is then called as impedance, which is then called as impedance. It is also measured in ohms only. Impedance is basically this. This is basically your impedance, Z. R square plus XL minus XC whole square, whole thing under the root. If you're wondering how to remember this formula, let me tell you, it actually is very much similar to the phasor diagram for voltages. So just like you have drawn before, do the same thing again here, but instead of voltages, do it for resistances and reactances. See how I'm doing it. Observe carefully. First, first show your normal resistance in phase with the current. Then inductors reactance, show it on the top. Capacitors reactance, show it below. Instead of voltages, you are now showing reactances. That's how it will be. Just see, it's very much similar. Voltage is replaced by reactances. Yes, instead of voltage of resistance, now you have just the resistance. Now take care of them. How? What is going to be remaining is just this much, which will be XL minus XC, and this will be just your resistance. This will be your current, of course. The resultant of these two, the resultant of these two by parallelogram of law of vector addition, that will be your Z. And still this will be phi only. So still you can say tan of phi is XL minus XC, whole thing divided by R. You can also see cos of phi adjacent by hypotenuse, which means it will be resistance by impedance. So all these things you can say geometrically, even for resistances. Not many people know this trick for resistances, so I'm giving it to you over here. It is valid here also, valid even for resistances. Is this clear? Yeah, we are using Pythagoras. Awesome, awesome, great. Cool. Now that we have understood that, okay, we can't add the voltages, amplitudes directly, instantaneous, yes. We have to actually add the voltages like phasors, meaning you have to treat them like vectors. So you need to know who leads, who is behind. And that's why this phasor diagram is very crucial. If you ever forget, sir, inductor was on the top or capacitor was on the top, then I'll tell you a simple thing. Remember this line, love is above everything. Love in this world is above everything. So love for inductor, L is above everything, and resistor, Pavam fellow, always is with the current. So the only person left over is C, capacitor. So capacitor is below over here. Okay, so that's how easy it is to remember it. Great. Now you might be wondering, sir, what about the power loss in this circuit? What about the power which will be lost in this particular circuit? So if you want to calculate the power in this circuit, the logic goes like this. Say, for example, P will be only lost across the resistor, because I have already told you across the inductor and capacitor, losses can't happen. Capacitor and inductor are energy storing devices. Faithfully, they will store in electric magnetic fields. They can give it back also. In fact, there is energy formula also, half CV square, half Li square. These are energy stored in capacitors and inductors. So there is no way a loss can occur inside an inductor or a capacitor. So the entire power of an AC circuit, the entire power of a AC circuit is always delivered across the resistor. But how much is the power across the resistor? Well, that logic, I can go back a little bit over here and see. I just told you what is the meaning of RMS. In order to find the power across an AC circuit, to find how much heat is generated or how much heat is generated per unit time in an AC circuit, you find out that constant current which will generate the heat, your job is done. And we found out that if you take a sinusoidal voltage or current, the RMS current is I naught by root 2. Oh, so basically, can I not just say this power loss across the resistor will be I RMS square into the resistance? So this is your power in the AC. Is this clear? I RMS square into the resistance. But then I might generally not have RMS value of the current or the resistance directly. Sometimes it is given in a slightly different form, maybe voltages is given. So what to do in such case? No worries, we'll just manipulate this formula. I'll just write it down like this. I'll write it down as IRMS into IRMS into R. Now IRMS, can I write it as VRMS divided by Z? Obviously, current is voltage by resistance. Check this out. Where did it go? Current is voltage by resistance, but resistance over here is impedance. This is the total voltage, this is the total resistance, which is called as the impedance. Okay, so I can just say the total current in the circuit is the total voltage by the impedance as it is into IRMS into R. Now what I will do, I'll write it as VRMS into IRMS into R by Z deliberately. So this will become VRMS into current RMS into what is this? Come on, think and tell me quickly. You can go behind in your notes and quickly you will be able to see what is that. Just see what is R by Z actually going to be. Come on, my dear warriors. R by Z. I think we did it just over here. R by Z is just going to be adjacent by hypotenuse, which is R by Z cos phi. Yep, perfect. So this is going to be cos of phi. So this is also another way of finding the power in an AC circuit. VRMS into IRMS into cos of phi. This cos phi is also called as the power factor of AC. This is also called as the power factor of AC circuits. Yep. Both formulas are perfectly fine. Nothing wrong in it. Both are perfectly fine. Cool. Now, what happens is you make a geometrical figure for this power calculations called as the power triangle, which looks something like this. Sure, I will write VRMS, 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 IRMS. That's it. If I just multiply voltage with current, I should get the power. But that's okay, only for DC, not for AC. Because in AC, voltage and current don't go up and down together. There is a phase delay, phase gap between them. So if some idiot just multiplies voltage and current and says that is power, that person is definitely wrong. So what that person has calculated is something called as apparent power. apparent power. It is not real power. So that is basically your apparent power, which is just Vrms into Irms. But the true power is Vrms RMS. If I take cos phi component of it, if I multiply it by cos phi, this side length is V into I. So V into I is cos phi. That is going to be my real power. That is going to be my real power, which is actually lost in the circuit. So this is apparent power, this is real power. Sometimes you will also do this Vrms, Irms, and find out the other component on the other side. So this is opposite, so this will be sine. So I will multiply it by sine of phi. This is not a real power. This is basically called as reactive power. Reactive power. Reactive power. Is that okay? Hello, Abhinesh. This is called reactive power. So this is called as a power triangle. Also keep in mind, in this reactive power, you will also see just this much also being called as the wattless current. Wattless current. The current which does not cause any power losses, that is called as the wattless. Watt means the unit of power. So wattless means it is not causing any power loss. So that is why it is called wattless current component, Irms into sine phi. This whole thing as such was called reactive power. This whole thing. Okay. This thing, whole, yes, this was called real power. That is your power triangle. Okay, great. Now, there is a very interesting thing which happens when you realize that actually, if I change the frequency of the AC source, just imagine the speed of rotation, the frequency. If I change it, I can change the resistances of capacitor and inductor. Yes, if I increase the frequency, then inductor's reactance will increase. Whereas for capacitor, because omega is below, the reactance will decrease. So I can play around with the resistances by adjusting the frequency of the source. And for different frequencies, I will get different reactances. The lengths will change, obviously. Z will also change, obviously. Phi can also change. And you will also see that the current will also change in that particular circuit. Now, if you draw that particular graph, that's a very interesting one, where here you have omega of the AC source, and here you have the current in the circuit. That graph goes like this and goes like that. It goes till a maximum value, it goes till a maximum value, and then starts dropping down. Which means when I change the frequency from a very low value to a slightly higher value, then the current in the circuit slowly increases before reaching a maximum and then dropping down. This particular time when it reaches that particular maximum value is of particular interest to me. So let me just mark it over here. Let me just mark it over here. This, when it happens, basically you have maximum current in the circuit. When will that exactly happen? let's go back over here a little bit and try to figure out from here only. If I want the current to be maximum, voltage can't be changed. That means impedance should be minimum, yes or no? If current has to be maximum, impedance should be minimum. Okay, let's come back to impedance formula. What is the formula for impedance? This is the formula. If I want Z to be very less, I can't change the resistance, but I can only change omega. Remember that, frequency. So, resistance square plus something is impedance. I want to make the impedance low. I can't change this, but something is added over here. So, to keep this minimum, shouldn't this guy be actually 0? XL minus XC, if it is 0, then I'm adding 0 to it. That's the smallest number which I can add. That is 0 to R square. So then the total value of Z will be the least. Yes or no? Everybody with me? So therefore, that maximum current happens. Therefore, that maximum current happens when, so therefore, I can say for maximum, for I max, Z is minimum. Z is minimum when basically XL minus XC is equal to 0. So therefore, your Z, which was typically root R square plus XL minus XC whole square, that whole term will go and you will be just left with R. So that is the least value of Z. That's when the current is also going to be maximum in amount. And because XL minus XC is 0, therefore it just means XL is equal to XC. XL is nothing but omega L. XC is nothing but 1 by omega C. So therefore omega into omega is 1 by LC, or I can therefore say that the omega is 1 over root LC. So when this happens, then the current is maximum. So the value of omega over here is 1 over root LC. This phenomena for maximum current when the frequency matches 1 by root of LC, that is called as resonance. That is basically called as resonance. Absolutely clear. Very good. And interesting thing over here is that if you draw the phasor diagram, it will look something like this, because XL and XC are equal. It will look something like this. This side will be equal to this side. The impedance will fall onto this. So Z will be here. Resistance will be here. XC is here. XL is here. If you similarly draw for voltages also, VL, VC, VR, this is the total voltage. Yep. So this is V naught, this is VR naught, this and this will be equal. This is VL naught, this is VC naught. Obviously, the current phasor was somewhere here. That was your current. And in both the cases, what do you see? Phi will be 0 because voltage and current are in the same phase. So phi will be 0. Therefore, the power factor which is cos of phi, which is cos of 0, that will be equal to 1. And 1 is the maximum value of the power factor. So maximum power is going to be delivered in the AC circuit at resonance. Maximum current, maximum power, least impedance, the highest delivery of the power is going to happen. Everything is going to be in sync. Voltage and current will be in sync because XL, XC, VL naught, VC naught, they will end up cancelling out each other. Is this clear, everyone? Sir, I've studied all the concepts of grade 12th. How can I revise any plan? Myths. If you have studied everything, as of now, I would say you have enough amount of PYQs in the last 5-6 years. Start practicing those PYQs. If you have some additional coaching material, use that. Else use DPPs for chapter specific improvement. Maybe you want to improve in a particular sub concept or a topic or a mixed question of certain type. You have to use a specific module or DPP or assignment or whatever coaching modules you have. That's what you should do. And mainly practice PYQs, PYQs, PYQs. Don't give mock tests as you can give mock tests, but you should give mock tests, but don't give too many mock tests because mock tests might just demotivate you. Right now, you're still in November. Till December, practice a lot of questions, improvise your theory concepts and the application and problem solving skills. You should be able to solve all models of questions. The exam strategy comes later on. For now, just concentrate on models of the questions. Improvise on your weaknesses and also strengthen your strong points. That's what I would say. DNC, welcome, my dear student from Kerala. A lot of students from Kerala. PYQ is not necessarily enough for 99 percentile. Okay, you need to go a little bit beyond that. Just don't do PYQs because I have a feeling this year physics might be, I don't know, it's just a feeling. Maybe I'm wrong, right? Physics might be a little tougher than the last years. So just doing the last few year PYQs might not help. You will think that, oh, physics will be easy, but then the physics comes difficult. Maths will still be tough. Chemistry might be slightly different, maybe slightly difficult too, who knows? And then if chemistry is slightly difficult, you might again get fooled. That's the reason why I'm saying go beyond PYQs. Okay. Now, the last concept in this particular chapter is the concept of something called as transformers. Yeah, you can do some JEE advanced or old JEE mains questions. Old JEE mains questions, very good level. If you see 2010, 12, 14, 15, like that, those old papers, right? They are very good. Even the AIEEE questions were good that time. AIEEE was the exam which was replaced by JEE mains. See, imagine there is a hydropower plant. So there is a waterfall. Okay. So this is water. Water is falling on a turbine, let's say over here. So what will happen is this particular turbine will rotate, and this turbine might be attached to a coil which is placed in some magnetic field, and because there could be some kind of so magnet might be there, and because this coil will rotate, it will generate some electricity, and usually that electricity which is generated from here, so this is basically your AC generation which will happen. And remember, the formula for that is E is equal to E naught, or magnetic field area of the coil, angular speed into number of turns, sine omega t. So that was the formula. You have learned that in electromagnetic induction. So an AC current is generated, but this AC current voltages which are generated, typically you will see they are of very low voltage. They are of very low voltage. So I'll just put it over here. So it's low in voltage, but typically the current is very, very high. Very, very high current is being generated from the generator plant. Now, just imagine if this current is passed from the main generation plant to the city, this high current and the resistance of the wire, I squared R, I is very large, resistance, even though it is small, because the current is very large, lot of power loss will happen. What will happen? Lot of power loss will happen. Correct? I hope this is absolutely clear. We'll be doing problem revision on this channel starting December. Wait for it. Revision is starting on this channel. But problem wise, the theory and the other model application questions and as well as the mock tests, everything will happen in the crash course. The problem discussions will happen on YouTube. Yep, revision wise. So in order to minimize the power loss, what is done? What is done is you use a device. Yep, you will use a device over here which is going to be called as a step up transformer. This step up transformer, what it does is this low voltage, it makes it into high voltage, and as a consequence, something has to go down. The current, low current is being generated. Low current is being generated. So now what happens is this low current will have very low, so there will be very low I squared R of the wire loss. There is very low power loss in these wires during the transmission. During the transmission. So it will be pumped, the voltage is pumped up. As a consequence, the current comes down because everything can't be increasing. And once this happens, you cannot expect such a high voltage in your house. Once you have reached the city, the exact reverse process will happen, of course, in the city. And here you have something called as the down, step down transformer. And this step down transformer is what is again going to make it low voltage and again high current. High current. And this current and this particular voltage will now enter your house. Will now enter your house. Yep. Will now enter your house or factory or whatever. This is what is given inside your house. So did you understand how the entire process of power generation to transmission to your final outcome in your household socket where the power comes? So there are a lot of steps which happen, and now we are going to study these things which are basically called transformers. So transformers are those devices which transform the voltage, meaning they either jack up the voltage or they put down the voltage. If it jacks it up, meaning it rises it, it is called as a step up transformer. If it pulls it down, then it is called as a step down transformer. Yes, then it is called step down transformer. Perfect. So, what is exactly there inside a transformer? Let's have a look at it. Hmm. So this is how a transformer looks like. You take a iron core laminated kind and you take a coil, you wind some number of turns. It is then called the primary side. The other side you again make a coil of different turns maybe. That is called as the secondary side. Primary is where the input is, output is on the secondary side. The input might have some voltage Vp, the output might have more voltage in case of a step up transformer. If it is low, then it is a step down transformer. Okay, fine. So the voltages will come here and here, it is developed here. As you can see, there is no physical connection between the two. How then is this voltage getting induced over here? It's because of the principle of EMI. Because think about it, the moment the current goes like this inside the primary, this current will definitely create a magnetic field inside that particular coil, and that magnetic field lines will start to pass like this from one side to the other, isn't it? The magnetic field lines will start to pass. These are the magnetic field lines. Because it's alternating current, once the current will go like this, then the current will go like this. So the magnetic field lines will go like this, then like that. So the magnetic field lines keep changing. Because of that, EMI, electromagnetic induction phenomena, happens and electricity gets induced in the secondary coil. So I can say an alternating current in the primary produces changing magnetic field, which by the principle of electromagnetic induction, your Faraday's and Lenz's law, you will see electricity is induced. Yes, EMF is induced in the secondary coil. That is the principle of working. Usually, what happens is the transformers might encounter some losses in this process, but the losses are kept as minimal as possible by ensuring none of the magnetic field lines escape or very few lines escape. If you have most of the lines passing through the secondary, so you have a very good flux which is linked between the primary and the secondary coils. So a very good EMF will be generated. So that's why you will see, to minimize the losses, to minimize the losses, what they do is number one, they use an iron core. They use an iron core which is basically ferromagnetic in nature to reduce the flux loss. To reduce basically the flux loss. You will also see that they might even laminate the core. They will even laminate the core to reduce basically the eddy current loss. Eddy current loss. Not just that, they might even use material with low hysteresis, materials with low hysteresis loss. Why hysteresis? Remember, hysteresis is that phenomena where you magnetize, demagnetize, and in this process of magnetization and demagnetization, some loss happens. Because the magnetic fields keeps on fluctuating, so this iron core also gets magnetized, demagnetized. So some energy is lost there. So if the hysteresis loop is very thin, losses are very less, then most of the energy will go over here. So the complete losses will be less, efficiency will be more. I hope this is absolutely clear. Yep. Is that clear, everyone? Awesome. Now, the formula which comes for this is as follows. Observe this very carefully. It goes like this. Voltage in the primary, number of turns in the primary, current in the primary. This is how it goes. Here, voltage in the secondary, number of turns in the secondary, current in the secondary. All these three will be equal. Yes. This is also sometimes called as the turns ratio, the ratio of the turns. Turns ratio. Primary voltage by secondary voltage is number of turns in primary by number of turns in secondary is number of is the current in secondary by current in primary. Only this part is inverted. That's all. Other than that, everything is fine. V1 by V2 is N1 by N2 is I2 by I1. That becomes the formula using the principles of electromagnetic induction. This is what you should know. Now, please remember one thing in this formula, that the main formula over here is only this much. The main formula is only this much. This comes only under a special condition, and this is only if, yes, only if there is a if over here. There is only a if it is 100% efficient. If it is 100% efficient transformer, only then you can write this complete equation. You will be like, sir, what if it is not? Say for example, it is, 60% efficient. 60% efficient. That means the power on the output or the power on the secondary side is 0.6 the power on the primary side. Is that clear? The power on the secondary side is 0.6 the power on the primary side. What is the power on the primary side? Power is voltage into current. So it will be nothing but Vp into Ip. Power on the secondary, power is again voltage into current. Okay, this is equal to 0.6. 0.6 is 6 by 10, which is 3 by 5. So this will be 3 by 5. So rearranging it further, can you see if I put this properly? Well, Vp on the top, I want Vp on the top. I will take Vs below it. Vs below it. What do I get? Vs is below it. I will have Is on the top and I will get Ip over here. But there is this number, yes, 5 by 3 into 5 by 3. So Vp by Vs is 5 times Is by 3 times Ip. Do you see this number has changed? So this is why I said this is only true if it is 100% efficient, then it will be 1 Is by 1 Ip. If it is not, then there will be some number fraction which will come over here. So that is why I have put that star mark. Is this absolutely clear? Everyone? Cool. Very, very important part of the transformer. So that is all that is there, and they have given some theory points about what are transformers losses, etc., where it is used, how it minimizes the losses, this power distribution in your NCERT also, so you can have a look at it. But other than that, nothing great in this particular chapter. So we have done the theory part. I know you want more problems, and we will do problems in a separate class. Like I said, we'll be doing problem practice in the month of December. So full support for your side is needed right now. I think the heat, temperature, calorimetry, KTG, thermo will be over this week. So yeah, the roar series should be completed. If you want fluids, you can just go back to nurture series and have a look at it. Other than that, every other chapter is completed from physics over here. So let's get back to problem solving, revision, and mastering more complex questions, and even the easy kill questions we should be able to crack it, so that we do it on time with some tricks and with some shortcuts and all of that. So that is what is going to happen. So stay tuned on the channel. So stay subscribed, or else you will miss out on all the important content. And trust me, Shreyas sir is known to produce results, which means you have to stay tuned till the end, or else you will be missing out on a lot of golden opportunities in your way for the next couple of months. And I want you to crack the JEE mains in the first attempt itself. I don't want you to give a second chance, because I want you to focus on boards and then advanced and other exams, I want you to be done and dusted in the first go itself, right? So leave a comment after this session is over. AC is mastered, so theory is done. Problem solving, obviously, like I said, we'll have a separate class. Have a great time. Take care. Hasta la vista. Bye bye. See you. Do not forget to like the video.